Hi viewers, in today's class I am going to discuss on helical antenna. So helical antenna is one of the important antennas that we have been used from earlier days. It belongs to the family of wire antenna. So it is operated in the frequency ranges of UHF, VHF bands, and it is also referred as broadband antenna whose frequency range is between 30 megahertz to 3 gigahertz. Here I have just shown the structure of the helical antenna. This is just having a simple ground plane for supporting, and from this end we will provide the antenna feed. See, this is the helix wire. The helix can be in the form of wire or it can be in the form of a tube, which is a conductor. Usually we'll just take a wire, and if we wound the wire in this way, automatically it will act like a helical antenna. The feed will be provided from this end, and based on the feeding, the current flows along the length of this wire. And here we have shown the different parameters of the antenna. This is basically used for the purpose of circular polarization. And as we know that many antennas output parameters depend on the different designing parameters what we have been using. In this case also, for helical antenna radiation property controlling, the main parameters are diameter as well as number of turnings, spacing between the loop, and the way how we excite the antenna. All these things will decide the output radiation pattern. This antenna provides high gain as well as the wider bandwidth. This antenna is operated basically in two modes, that are normal mode and as well as the axial mode. The normal mode importance is whenever we go for the smaller helix case, that is NL less than lambda. That means the length of the helix is very small. N is nothing but the number of turnings and L is the length of the helix. Lambda is nothing but the wavelength, operating wavelength. Whenever the size of the helix is very smaller than this wavelength, then it leads to the normal mode of radiation, and this is shown in this figure. This is the output of the normal mode operation, where it can be referred for the broadside array case. In broadside antennas, as already we know, the radiation pattern will be perpendicular to the axis of antenna. Similarly, for in normal mode also, the radiation pattern will be perpendicular to the antenna axis. And the second case is axial mode of radiation. In axial mode of radiation, the output radiation pattern will be like this. It is maxima along the axis of the antenna. So this is straight away referred to end-fire array. So similar to end-fire array, this axial mode of antenna will be operated where we get the maxima radiation. And compared to normal mode, here the bandwidth and efficiency will be high. In normal mode case, the small bandwidth and low efficiency are overcome in the axial mode of operation. Here in this you can watch. So this is the helix and this is our ground plane. The helix operated in this direction produces the output in this particular direction. From this, what we can observe, the way how we orient our helical antenna, based on the orientation, we will be obtaining the output radiation pattern. See, all the combined radiation pattern will be available in this direction. All these three helix output. So, this type of operation, we call it as multi-filler, where many number of helix will be combinedly operated. As monofiller antennas means only single helix will be operated. So depending on the application, either of them will be chosen. So these things are the basic points related to our helical antenna. Basically, helical antenna's importance is for producing the circular polarization, right? In the next slide, we'll continue. So this is the structure of the helical antenna. In this structure, you can observe the some points. See here, this is the start of the helix point. Before this point, what we can observe is entire section is feeding section for your helical antenna. This feed section can be of two types. One is coaxial cable. The second one is transmission line. So here we have shown with coaxial cable. As we all of us know, coaxial cable has two conductors, one inner conductor and an outer conductor. This inner conductor itself provides the feed and it continues in the form of a helix like this. That means here this helical antenna is simply called as traveling wave antenna. Heard about this term? Traveling wave antenna, right? So in this traveling wave antenna, what happens? The current travels along the length of this helix like this, and here what happens? The current remains to be uniform throughout this helix, whereas the phase variations will be appearing. It travels along these directions. Because of this flow of current, what happens? The electric field will be produced here. With the effect of this electric field, automatically the radiation emits out. That appears as radiation pattern to us, right? So here in the structure of this helical antenna, some key points we need to observe that we'll see now. A helix is a three-dimensional geometric form where it is in the form of a straight line, circle as well as cylinder. How we get these three forms, we'll see. Say if this is the helix structure. If I just unwound these turnings, what I get? If I unwound these turnings, just I simply get a straight line, right? And out of these turnings, if I consider only single turn, what I get? A circle. If I combine a line and a circle, what I get? A cylinder, right? So these are the three geometric forms of a helical antenna. So as already we know, individually we will be operating this linear form of antennas as well as this circle or loop form of antennas. When we combine these two, we'll get a helical antenna structure. That is, in practical world, if you combine a loop antenna and a short dipole antenna, automatically we will get a helical antenna. That is the concept. Okay. So here for n number of turns of helix, the total length of antenna is referred as L. Okay. So here I am going to analyze this helical antenna with the help of a small geometric form. Let us take a right angle triangle form. Here you see here what is this as the separation distance between the turnings. So I have taken center position of these two as reference, and the separation or spacing between these two is referred as capital S, spacing between the helix. And next, what is this L? L is nothing but the length, L is nothing but the length of the helix. So length of the helix, we need to consider the total length of a single turn. Here, just observe carefully, our measurement should be like this. Total length of a complete turn. Okay. So that is referred to as capital L, like this. C is nothing but circumference. Actually here this outer diameter is referred as capital D. This is the diameter of entire helix, and this small d is the diameter of inner conductor. Don't get confused with small d and capital D. This is the diameter of entire helix. This is the diameter of the inner conductor. Next here, the helix will be starting from this point. Before this, it acts like just a feed wire, right? So using these three parameters, we have formed a right angle triangle. Here you can find a new parameter alpha. What is this alpha actually? Alpha is nothing but it is a pitch angle. It can be defined as it is nothing but the angle between a line tangent to helical axis and a plane normal to helical axis. For example, this is the axis of helical antenna. This one, right? Axis of helical antenna. If I take this as axis, a line tangential to helix axis and a plane normal to helix axis. The separation angle between those two is nothing but pitch angle, like this. Okay. So this we refer as L, S, L and C. So from this, what we can say is this pitch angle is a most important deciding factor of the helical antenna output. As in the first slide already we said that the radiation properties and polarization of the helical antenna are dependent on these three major factors. So here you can observe length of a turn is referred as L, spacing as S, and pitch angle as alpha, and circumference with pi d, right? So the radiation characters of antenna are changed by varying these parameters. So depending on these parameters, the polarization also can be decided, whether it is circular polarization or linear polarization. Okay. Now we are going to discuss on types of modes of helical antenna. Basically, we are having two modes, that is normal mode and axial mode, as we have seen in first slide. So normal mode, when it is operated, that already we know. Whenever the case is smaller helix, that means if we take the case of small helix, then it will be operated in normal mode, as we are shown here. N, L less than lambda. N is number of terms, L is length of helix, and lambda is wavelength of operation. In this case, what we get, the radiation field is maxima, and it is whenever it is maxima, it is perpendicular to axis, and minima along the axis of antenna. Say for suppose this is a helical antenna, perpendicular to its axis we get the maxima radiations, and along the axis we have minima radiation. So say suppose the size of helix is very small, in that case we achieve the normal mode of radiation, and this is simply referred to broadside array case, and it is also called as perpendicular mode of operation. In this case, as the length and size of helix is small, automatically what happens, radiation efficiency will be low and bandwidth also will be very low. Because of these two conditions, we need to again go for the other mode of operation. Before going to that, we'll analyze this case. See here the limiting conditions of the helical antenna. So what are the limiting conditions of the helical antenna? We'll get from here. See, in the first diagram, we have shown only loop antenna case. In the second one, short dipole case. So already we know our helical antenna is combination of loop plus short dipole. Whenever I get a loop, just imagine or think a helical antenna is combination of some loops and entire dipole. We can take like this, some small short dipoles. So whenever I am having the loop means, what does it mean? In that case, there is no spacing concept. If this is my right angle triangle, this is alpha, S, L. Whenever S is 0, automatically what happens? Alpha tends to 0. S0 means alpha goes to 0. In that case, what happens? We will have the loop concept. That means no separation or spacing between the helix. Only single loop or turn will be present. This case is the loop antenna case. What is the second case? In this, we'll consider the separation of loops. That means S remains to be constant. S remains to be constant like this. So in this case, what happens? There is no question of loop. We'll majorly focus on alpha maxima 90 degrees. And in this case, the diameter tends to 0 and S remains to be constant. So here short dipole will be dominating. So short dipole case means some amount of separation between the turns. This will be dominating factor. So from these two, what we can say, the limiting condition for pitch angle lies between 0 and 90 degrees. When it is 0, it goes to loop. When it is 90, it goes to short dipole case. So in practical world, when we make it as 0, it acts just like loop antenna. When it is make it as 90, it acts like short dipole. But what we need, the combination of both. That means loop and short dipole combination is nothing but a helical antenna. So we need to operate our helical antenna in between 0 and 90, not go to limiting cases. Okay. So whenever we start, using the series or some combination of loops and short dipoles, automatically they will become a helical antenna. So the main concept of helical antenna is to achieve the circular polarization. In the next, we will see how we can do that. So here, what happens, just look here. Helical antenna can be considered of having number of small loops and short dipoles. So here what is happening? You are having number of small loops and short dipoles connected in series. That means in helical antenna, what happens? These are the number of loops and short dipoles. So if these are connected like a series form, then automatically it acts like a helical antenna. So we will analyze the field equations. The first one is small loop field equation, short dipole field equation. So these field equations we can see in the second unit of antenna subject. Their derivations will be available. I have directly taken the equations. So the field equation for small loop antenna is 120 pi square into I sin theta a by r lambda square. For short dipole case, E theta is equal to j60 pi into I sin theta s by r lambda. So in this case, to analyze the helical antenna, we'll go with axial ratio. So axial ratio is nothing but the ratio of these two fields. So if I take the ratio of both of them, most of the terms get cancelled. Finally, I'll have my AR value as 2s lambda by pi square d square, where we know that A is equal to pi d square by 4. Just substitute that, we'll be getting this one. In circular polarization, elliptical polarization, we'll study with 3 cases. So first we'll go with AR is equal to 0 case. When my axial ratio is 0, what does it indicate? AR is becoming 0 means what is happening? S tends to 0. As just now we have seen, what happens when S tends to 0? Your short dipole goes to 0. In that case, loop antenna will be dominating. Whenever my operate in loop antenna mode, the type of polarization available is linear horizontal. And next case, what we are having, AR tends to infinity. What does it mean? In this case, A tends to 0. A tends to 0 is nothing but D tends to 0, which leads to the dominating part is short dipole. So in this case, the loop will be negligible. It operates in short dipole antenna mode. In that case, it leads to linear vertical polarization. So whenever, if you observe here, what is happening? Either 0 or infinity. These two are like limiting cases. And instead of those two, if I equally operate both cases, that is short dipole case, loop antenna case, it leads to circular polarization, where your axial ratio is equal to 1. In this case, both short dipole and loop are equally contributed. No dominating. Both will be in equal electric fields, right? So in that case, the output radiation pattern will be in circular polarized mode. So as we say that your axial ratio is equal to 1, if you equalize these two equations, finally what we get, alpha is equal to tan inverse of C by 2 lambda, right? So finally, we are going to discuss about axial mode of radiation. So axial mode of radiation case, why we are going is, as already I said, in normal mode of operation, as our length or size of helix is small, what we have seen is there the efficiency and bandwidth are low. But in axial mode of radiation case, what happens is your size of helix is larger. So because of that, what happens, our radiation efficiency will be increased as well as bandwidth of operation will be high. This case, it is referred to as end-fire array mode. And here the maximum also we achieve along the axial direction, helical axial direction. So this we will call it as end-fire mode of operation also. In this, the circumference of helix should be always in a range of one wavelength, and spacing should be between lambda by 4. So here in the diagram, we have specified all the parameters, as the spacing between the ground plane and helix always should be lambda by 8, and the entire length of ground plane should be 0.8 lambda, and spacing should be lambda by 3. Here the total diameter should be lambda by 3. Okay. So the pitch angle range also we have specified here. It should be between 12 degrees to 18 degrees. Already we said that pitch angle should not go to extreme cases. It should be in between the range of 0 and 90, and 14 degrees is chosen as optimum angle case. As the length of the helix decides the gain and the bandwidth of the antenna. So these are the different parameters related to axial mode of operation. In practical world, compared to normal mode of operation, axial mode is operated in the wide range. I shall just list out the applications of the helical antenna. Its circular polarization is majorly used for satellite and space applications related to space telemetry, and it is used for collecting the data from moon to earth, and in missiles in different areas it is widely used because of its circular polarization concept. Thank you.